So now that we know about the first and the second law, let's discuss perpetual motion machines. What do we see here? Well, we see here a system, right, with system boundary here, in which we've got heat out and work out, right? So what's happening inside the system? Well, let's see. We've got this boiler that's being resistively heated, generating steam, turning a turbine, dumping heat, repumping. This turbine is turning a generator, which is generating electricity, which is used to do some work out here and also used to heat this boiler. Now, this seems like a pretty neat system, but this is what's called a perpetual motion machine of the first type. So this violates the first law of thermodynamics, right? We've got this system that is creating work, right? It's outputting work and it's outputting heat. So this is a net energy creator. And you can see this is violates the first law, which says that energy can neither be created or destroyed, right? So it's creating energy. A device that violates the second law is a perpetual motion machine of the second type. So let's look at that. Here's an example. We have a similar system to the first one, except now we've gotten rid of the condenser, and we're putting heat in. We're boiling the steam. We're creating, work through the turbine, and then we're recycling this, pumping this up, and reboiling. Right. So we have net work out, and we've got heat going in. So this is an example of violating the second law of thermodynamics, right? 100% conversion of this heat into work. And the thing about perpetual motion machines is they sound pretty good. And if something sounds too good to be true, well, it probably is. So that's the second law. You can't get something for nothing. All right, let's talk about reversible and irreversible processes. Reversible process. Process that can be reversed without leaving any trace on the surroundings. And these would be considered reversible processes over here. Something like a frictionless pendulum, right? There's no loss to the environment of of energy to friction, right? And a quasi-equilibrium expansion of or compression of a gas. So very, very slow equilibrium process. An irreversible process is a process that is not reversible, right? So it results in some change that's irreversible to the environment or to the system. And basically every process that occurs in nature is irreversible. So why the heck would we want to even look at reversible processes? And the reason is, well, number one, reversible processes are easy to analyze, and they're sort of an idealized model, right? It's the theoretical limit of what you could possibly get out of a process. So it represents sort of the best case scenario that you could possibly get out of an actual process. And some processes are more irreversible than others. And of course, we try to approximate reversible processes, primarily, again, because of the analysis. It makes the analysis much easier if we approximate it as a reversible process. So let's look at, this is sort of a nice example of how you could envision why something is irreversible or not. So here's a very slow, a reversible process that tells you first delivers the most and consumes the least amount of work, right? So these represent the theoretical upper limit. It's the best you could get, either the most work out or it consumes the least work. So here are some examples of slow reversible processes, right? Here you have an expansion. Maybe you start off here with water filled up, and you allow this gate to freely move as the water pushes it, right, that way. So you're expanding slowly, right? On the other hand, you can have a slow compression, right, where you're pushing this and you're lifting the water back up. and you could cycle back and forth between these. These are very slow, reversible processes. Then you could have something like this, a very fast process where you expand quickly, right? So, or you compress quickly. And what happens here? Well, if you all of a sudden expand very quickly, you move this gate faster than the water can change positions, right? So what do you get? You get a lot of sloshing in here, right? The water is going to change position rapidly, elevation rapidly. It's going to start sloshing, and you're going to lose a lot of energy to this sloshing in the water, right? Same thing with compression. You can compress this quickly and basically generate a tidal wave, right? And that's going to generate a lot of, again, disturbance, turbulence in the water, and it's going to push back on your wall as well. Oh, this is an interesting slide. So, what causes a process to be irreversible? It's something called irreversibilities, right? And what are those? Things like friction, unrestrained expansion, right? Like we saw the water where we moved the wall really quickly. Mixing of two fluids. You can't, once you dissolve sugar in water, that's an irreversible process. It's not ideal. You need to do something to separate those two. Heat transfer across a finite temperature difference. Electrical resistance, inelastic deformation of solids, chemical reactions. These are all irreversible. So yeah, the presence of any one of these makes that process irreversible. Here's an example of friction, right? You have a gas expanding a piston, and just the frictional loss between the piston and the wall, that's enough to render it irreversible. Here you have compression and expansion. So we talked about this in the context of the water. Do the same thing with gas, right? A fast compression or a fast expansion. These are both irreversible processes. And then you have the extreme case, an unrestrained expansion, where you've got this, say you got this membrane that separates a high pressure from a low pressure, and this fails, this gets punctured somehow, and all of a sudden you have a rapid expansion of gas. This would be like a safety release valve. Yeah, heat transfer through a temperature difference is irreversible, right? So for example, you've got this can of soda, you take it out of the refrigerator at 5 degrees C, you put it on the counter, and heat is transferred to it from the surroundings, and at some point it reaches 20 degrees C. And then it's a nice warm soda. And the reverse process is impossible, right? This is irreversible, but this is impossible. This is taking a soda can out at 5 degrees C and in a 20 degrees C environment, and it cools from 5 to 2 degrees C. This is an impossible heat transfer feat. All right, so let's look at some internally and externally reversible processes. So something that's internally reversible is if there's no irreversibilities within the boundary of the system during the process. So for example, if you're looking at the system in here and there's no irreversibilities, then this is an internally reversible process. If you have no irreversibilities outside the system, that's called an externally reversible system. And then a totally reversible system or process involves cases where it's both irreversible within the system and outside the system with its surroundings. Basically, total reversible system has it's no heat transfer through a finite temperature difference. There's no non-quasi-equilibrium changes. So everything's quasi-equilibrium, very slow, right? And then no friction or other dissipative effects. Now remember, in thermodynamics, we're concerned about difference between states. So we can say it goes from state 1 to state 2 as a reversible process, even though the actual process may not be reversible. And that's part of idealizing the system that you're trying to model. All right, so here's a totally and internally reversible heat transfer process. So this one over here, you've got, say, a phase change from a liquid to a vapor, a very slow process, or you're doing this very slowly, and you're applying heat to the system. But notice, this is 20 degrees C in here, and you've got this in contact with a thermal reservoir that's at 20.00000, etc., 1 degree C. So it's infinitesimally smaller or larger than the temperature inside, right? But it's just enough to provide a little bit of heat transfer to cause that evaporation to happen. Again, very, very slowly. This is internally reversible, but because we're changing phase slowly. However, the externally it's not. Externally it's irreversible because we have here a thermal reservoir at 30 degrees C, and we're transferring heat quickly. So externally, this is a irreversible process, but it's internally reversible.